So I ended the previous half with a kind of a pessimistic conclusion that, well, these ideas of passively protecting information using DFSs and other subsystems can only take us that far, because when we have symmetry breaking, then information starts to be corrupted, and we need a way to deal with this problem. So in a way, it's clear that a DFS or a northern subsystem can only be kind of a bottom layer of protection. Okay, but it's a useful layer of protection if there is some symmetry or partial symmetry. Some symmetry, like what we saw with the ion traps. We have long wavelength phonons. We should use it. We can't expect that this is going to be a panacea and it's going to be the end of all our troubles. But it's a useful thing to do. And the other good reason to be interested in decoherence of subspaces and other subsystems, etc., is what I talked about in the very beginning, which is that they do provide a way to think about error correction in a unified way. So even if there is no perfect DFS or the subsystem, you can think of error correction as being a protection, passive protection, when you include the recovery method in the process. Now I'm going to start to talk about politics. There's 50 seconds left till this thing explodes, apparently.
Someone has to protect shut down.
Good joke, anyone?
We'll fix it in post.
Yeah.
How long until the trash is?
Alright. Sorry to disappoint those who thought they could already go home. And you get to stay through the second part. Okay. So the idea for dealing with this problem of symmetry breaking, if you wish, one way to deal with it is to borrow from nuclear magnetic resonance, from NMR. And there's a trick in NMR that was developed by Erwin Hahn in 1950, which has become extremely relevant. It's called the spin echo effect. And it's sort of the basis for what I'll be talking about for the second half today. So what is the spin echo effect? Well, imagine that we have some runners, which are a metaphor for some spins on the ball sphere. And these runners are all starting out at the origin at time t equals 0, but they run at different speeds. Okay, so over here, they're in a coherent state. And then as they start to run, they decohere because they run at different speeds. So this is like a bunch of spin 1/2s, let's say, that are processing at different speeds because they're coupled to different local environments. But now, rather than give up, here's what we can do. We can try to instantaneously flip all these runners around. So they run in a certain direction, and then they turn around 180 degrees, and they start running back. Okay. So obviously, if they all turn around instantaneously and then start running back at the same speed that they were running at to begin with, then they will recohere at the origin. They will all get back together at the origin. So we will once again have a coherent state. Okay. So this is the idea of the spin echo. And here is I believe, the first trace of the very first spin echo experiment ever performed by Erwin Hahn, in which he saw an echo after applying precisely this kind of scheme the act of turning the runners around, of flipping the spins around, is to apply a 180-degree pulse along the appropriate axis. So here's just another way to see it. In spin language, you have a collection of spins that are pointing up on the Gauss sphere toward the North Pole, or sitting on the North Pole. The first thing you do is you prepare them in the XY plane by giving a 90-degree pulse. And then they start to dephase. So the F stands for the fast spins and the slow spins. They're rotating in this direction. And then you flip their direction around, just like you did with the runners. So rather than going clockwise, they got flipped around by 180 degrees, and they recohere at the origin. Okay, and then it happens again. They start to dephase again. So you get this kind of a stroboscopic recoherence, or rephasing. Every time everybody comes together again, and you get your system back. Well, you don't get it back perfectly, as you can say as you can see in Hans' experiment. And a big chunk of what I want to talk about is how to deal with this. What is this? Maybe 10% fidelity, and we need to get 6 nines. Okay, so how do we get 6 nines out of this kind of concept? So that's one schematic way to think about what dynamic decoupling is, and I promise that I will explain how it's related to symmetry breaking and basically restoring broken symmetry, so that's coming, but we're not ready yet. First, I just want to present the idea again, the very same idea, just slightly more formally. So what is it that we're actually doing formally? We have a system bath Hamiltonian, and what we're trying to do is we are trying to time reverse. Time reversal is equivalent to putting a minus sign in front of the Hamiltonian. Right? So when the runners are going this way and you do this, that's like time reversal. Everybody's running back to where they were. So that's what we're trying to do. We're trying to put a minus sign in front of the Hamiltonian. That's time reversal. In other words, we're looking for an operator, P, a unitary operator, that's the pulse, so kind of a unitary transformation, which anti-commutes with the system bath Hamiltonian. And then we're going to apply it. This is time. We apply a pulse, P, evolve, apply the opposite pulse, evolve, and this operation of evolution pulse is supposed to give us the net effect of having gone back to the origin, i.e. of having implemented the identity transformation. So the math is here. Let's say that you evolve under the system bath Hamiltonian for some time tau. Now you apply the pulse, evolve again, apply the pulse, and now it's an identity that you can easily prove that you can take a unitary and put it inside the exponential. P, unitary P dagger, the P goes inside the exponential. Okay, just by Taylor extending the exponential, you can prove that in one line. So I put the P inside, but we assume that P dagger is negative H, so that's why this minus sign disappears, becomes a plus sign. Now these two operators cancel, and we get identity. Okay, so this identity is exactly this going back to the origin. The net effect is that nothing happened. Now, if we could do this in real life, then we would have totally canceled the effect of the system bath Hamiltonian, and we would have perfectly restored our coherence. But of course, there's a whole bunch of cheating going on in these lines that I wrote here. For example, I forgot about bath Hamiltonian. I assumed that the pulses are instantaneous, which is impossible. That requires infinite energy. All sorts of problems, okay? But in a way, this is the essence of the idea. And once again, I want to see how close I can get to this idealization in real life. Now here's a little example just to make it a bit more concrete. Let's say that we have a pure dephasing type of system bath interaction on a single qubit. Okay, so here's the qubit. It's operated on by the sigma z operator times the bath. What is the pulse that we would have to apply? Well, we would have to apply x pulse, because x anti-commutes with z. That's this condition. Right? So an x pi pulse is the time reversal operation for pure dephasing. All right, and here's yet another way to look at it, kind of a geometric way. which will let us realize that we're not limited to doing time reversal. Time reversal is when you imagine that you could put the system bath Hamiltonian on some sphere. You can actually do that for a single qubit. The system part of the system bath Hamiltonian can be thought of as an operator on the Bloch sphere. But think of it just as a nice picture, if you wish. Time reversal is the operation of flipping the Hamiltonian to be on the opposite side. And if you do this over and over again, the average of these two vectors is 0. So it's as if the system bath Hamiltonian just got averaged to 0 and it's gone. But if you think about it in these terms, you realize that time reversal is not the only thing you can do. How about putting the Hamiltonian on the vertices of a tetrahedron? All right, so we can do this. It's been averaged onto the vertices of the tetrahedron. Still, these vectors, these 4 vectors, which I arrived at by applying pulses, appropriate pulses, these wouldn't be pi pulses, it was some other kind of pulses. The average effect here is that once again the system bath Hamiltonian has gone effectively to 0. And of course, once you realize this, you realize that you could just try to find pulses which take you to any symmetric object on the Bloch sphere. Or in fact, how about just random? Right? If you just randomly rotate the Hamiltonian around, then it will be ergodically averaged to 0. So that's another effective strategy. In fact, it's a really good idea, this random method. When you have a Hamiltonian that you know nothing about, which can be the case, then this is pretty much your best bet. So there are many ways in which we can average to 0, but I'm going to stick primarily with this notion of time reversal. Okay, so how is this related to restoring a broken symmetry? Well, let's say that we have, let's go back to 2-qubit dephasing. Now, when I was talking about decoherence-free subspaces, I assumed that the dephasing system bath Hamiltonian was collective, meaning that we had sigma 1z plus 2 sigma plus sigma 2z coupled to a single bath operator. Now let's assume that we have a general 2-qubit dephasing Hamiltonian. And now I want to somehow symmetrize it. I want to turn it into the collective dephasing Hamiltonian, for which we know that there is a decoherence-free subspace. So the first step is to just rewrite it as a sum of a difference and a sum. And now let's call this logical z, this operator. This is a logical z with respect to this logical x. Okay, you can check that these two operators anti-commute. Now, let's say that I have some kind of a quantum dot system where I have the ability to control an exchange Hamiltonian, not Heisenberg exchange, anisotropic exchange, where I can make the coefficients in front of the xx and yy terms different from the coefficient in front of the zz term. Okay, so imagine that this is some operator in a system Hamiltonian that I can control. So what I'm going to do is I'm going to try to use this x operator as a dynamical decoupling bang-bang type operator, just like in the previous slide, in order to time reverse this piece. Remember that x time reverses z? Okay? These two are anti-commuting operators, just like the regular Pauli sigma x and sigma z. These are just encoded sigma x and sigma z. So if we turn this x on and off by virtue of being able to do it in our quantum dot system, we can run this kind of a sequence. Let's start with the pulse, free evolution, pulse, free evolution, and then by the very same algebra that I showed in the previous slide when I just had a single qubit, this x is going to flip the sign of this z, and it will cancel this term. And what's going to be left is just this term, and this term is a collective dephasing term. You see here, the bath is coupled to the sum of sigma 1 and sigma 2, which was the collective dephasing scenario. So what we have now is that we have kind of stroboscopically generated a collective dephasing Hamiltonian. So stroboscopically, we have a decoherence-free qubit. Okay, so in this way, we can use the idea of dynamical decoupling of the spin echo in order to actually generate a symmetry where it wasn't there to begin with. So this is a trick that works to make collective dephasing. You might ask, well, what about something more general, like collective decoherence? And it turns out, without going into details, that rather amazingly, oops, sorry for the font mess up here, you could do the same thing for a general system bath Hamiltonian using the Heisenberg interaction. So we can use the Heisenberg interaction, pulsing it on and off in a certain way, allows us to take a general symmetry-less system bath Hamiltonian and turn it into a collective decoherence type Hamiltonian. And the details are given in these papers that involves rather lengthy sequences. But it's kind of remarkable because what this tells you is that not only can you perform universal computation with Heisenberg over the noise of subsystem codes and decoherence subspace codes, you can also generate the conditions for collective decoherence using Heisenberg. Okay, so this is why I'm calling Heisenberg super universal. It's not just universal over these codes, it can even be used in order to generate the conditions enabling this universality. So Heisenberg is pretty good stuff. Okay. Now, in order to actually formally analyze what goes on when we do dynamic decoupling, we need a detour. And so bear with me, this will be somewhat more mathematical. But what I'm trying to get at is a tool which will enable us to actually understand how to do the error analysis for dynamic decoupling. Okay, so we need to get a grip on what the errors are. So far I just threw around some formulas and I wasn't very careful. But I want to understand how the errors behave. Why is it that Han didn't see the full echo, so to speak? Okay, so very quickly, here again is the story of decoherence. Let's say that we have just an isolated system subject to some Hamiltonian H sub s, and it involves subject to the Schrodinger equation. Okay, so we get unitary solution. Here is the Schrodinger equation written for the unitary. And let's write this equivalently in terms of a density operator. Okay. Now, that was the isolated system. Now let's consider the open system. The open system, we have the joint system bath state evolving unitarily subject to the full unitary generated by the full Hamiltonian. And we're going to trace out the bath, the standard. Okay, so now what is decoherence? In the first part, I define decoherence as non-unitary evolution. Equivalently, I can say that decoherence is the scenario where the norm difference between the actual system state, the one that we get from the actual dynamics, including the system bath coupling, minus the state that we would get from ideal dynamics, when this difference is non-zero, greater than zero, it's norm, positive, semiductive. All right, so this is decoherence, when this difference is actually greater than zero. The question is, what is the right norm? And it seems like a perhaps boring technical question, but it turns out to be rather important in doing the analysis carefully, and it also has interesting connections to foundations. So what norm? Okay, how should I measure the difference between two density operators? The answer has to do with how we do quantum measurements. Quantum measurements give us probability distributions. Right? When you measure an observable, you get a probability distribution over its eigenvalues. So let's talk about how we distinguish classical probability distributions first. And one way to do that, which has good properties, is to use the so-called Kolmogorov distance, which is simply the sum of the absolute values of the differences between the two probability distributions. Okay, so I'm going to use this as my gold standard without justifying. There are good reasons to use this distance, but let's just accept it. All right, how is this related to quantum? Well, again, in a quantum setting, the most general measurement is a POVM, a positive operator value measure type measurement, which means that you have a set of positive operators, EI, which satisfy this condition which guarantees trace preservation. And when we have a system in some state rho, the probability of observing outcome I, given that the system is in state rho, is given by this standard formula, trace rho times the ith POVM operator. And that is the probability distribution. The piece of I is the probability distribution, given that the system was in state rho. Okay, so a quantum measurement produces a classical probability distribution. Now let's say that we have two density operators, rho 1 and rho 2, which is going to give us these two probability distributions. All right, we're going to perform the same measurement, the same POVM measurement on two different states. And the states I have in mind are the actual state due to the system bath evolution and the ideal state. So let's compare the measurement outcomes. And the measurement outcomes are, well, two probability distributions. Probability distribution P1 corresponding to state rho 1, P2 corresponding to rho 2. Okay, so I'm going to, in this part, I will need three lemmas. This is lemma number 1. And I'm not going to prove this lemma. You can look it up in Nielsen and Schwab. The lemma says that the Kolmogorov distance, which I'm going to call delta, is upper bounded by the so-called trace norm distance between the two states. Okay. Now what is the trace norm distance? The trace norm distance of an operator, the trace norm of an operator, is the trace of the square root of A dagger A, which is just the sum of the singular values, which is basically just a trace. The trace of the absolute value of A dagger A. Okay, so is there somebody who doesn't know what a singular value decomposition is? Okay, everybody's too shy to admit it. Think of singular values as eigenvalues in the case of Hermitian operators. All right, so the trace norm distance is an upper bound for the Kolmogorov distance. Okay, so instead of working with the Kolmogorov distance, which is hard to work with, we can instead work with this upper bound, the trace norm distance. Okay, and this bound, it turns out that it's actually tight in the sense that if you made the measurement which was able to optimally distinguish the two states, then this inequality would become an equality. Okay, so from now on I don't have to worry about Kolmogorov distance, I can work with the trace norm distance between my two states. Next, this is lemma number 2. This lemma says that rather than working with the trace norm distance between the reduced density matrices, where we have traced out the bath, we can work with the density matrices before tracing out the bath. And this lemma is actually very intuitive. It says that if you erase information, you decrease the distance. Here we have erased information. We've traced out the bath. We've averaged out the bath degree of freedom. So we've erased information. That decreased the distance between the states. Here's the proof. Here I have these two faces. This is also from Nielsen and Schwab. I wish I had invented this myself. This is after erasure. After erasure, on the left-hand side of this inequality, we cannot distinguish these two faces, right? But before erasure, they were actually different. Okay? So it shows you that the distance, here the distance is 0, here the distance is obviously not 0. Okay? So erasing information is a distance decreasing operation. Okay, so what does this mean for us? It means that instead of working with the trace norm distance over the system space, we can work with the trace norm distance over the system bath space. That's lemma number 2. Okay. Now let's compare ideal and actual, should have been system bath evolution. So here's the ideal system bath scenario. We don't have a coupling between them. HSB has been set to 0. That's an ideal case. The bath is evolving subject to some bath phenomena. But there's no coupling between them. Okay? So the system doesn't know that the bath is there. On the other hand, in real life, just like before, we do have a coupling. All right? So now we can look at the distance between the ideal state, which is up here with system valve turned off, and the actual state. All right, so now I'm exploiting the previous lemma, that I don't have to work in the reduced space. I can work in the joint system valve space. And I'm looking at the trace norm distance between the actual state and the ideal state. And I make use of the fact that the trace norm is so-called unitarily invariant. A unitarily invariant norm is one UI is one which is equal to, for all unitary U and V. Okay, so it's true that the trace norm distance is unitarily invariant. And what I've done is I've simply multiplied by US dagger UV dagger, which is a unitary operator. And that's my that's the operator. That's how I got the operator V. Okay, so I've simply removed from the ideal evolution. I've simply removed this trivial transformation by US tensor UV, and that's how I got the V operator. Now here's an important step. I'm going to define an effective Hamiltonian. This is some unitary operator. And I can always write this unitary operator as the exponential of -I times some Hermitian operator, right? So that's this effective Hamiltonian. It's not a real Hamiltonian. It doesn't actually generate the evolution in the sense of the Schrödinger equation. It's just some convenient effective Hamiltonian corresponding to this unitary. Okay. Now here's the third level, final level. It says that this trace norm distance is itself upper bounded. We don't need to take the exponential. We can actually erase the exponential. But then we have to replace this by the operator norm, which is another kind of unitarily invariant norm. The operator norm is just, for a Hermitian operator, it's just the largest eigenvalue. For a general operator, it's the largest singular value. Okay, so, and this H effective is in fact Hermitian, so just think of it as the largest eigenvalue. Okay, so and the proof is simple, but let's get it. So you want to turn off the slide? So now let's put all these three lemmas together and let's see what we got. Remember, I wanted to distinguish the measurement outcomes over two states, rho 1 and rho 2. The first lemma said that the Kolmogorov distance is upper bounded by the trace norm distance. The second lemma said that the trace norm distance in the reduced space is upper bounded by the trace norm distance in the full space. And the third lemma said that the trace norm distance is in fact upper bounded by T times the operator norm of the effective Hamiltonian. Okay, so let's put these three inequalities together. They all connect. And we get that the Kolmogorov distance, which is the distance between the measurement outcomes, any measurement you would make on these two states, the actual state and the ideal state, is upper bounded by T times the norm of the effective Hamiltonian, which is something that I want to call the noise strength. Okay, so why is this good? You'll see. We're going to use it in our dynamic decoupling analysis. But I also want to point out that the very same quantity, noise strength, shows up in the analysis of fault-tolerant quantum computation in the non-Markovian setting. And I don't know if this came up at all in Daniel Gaussman's talk. But okay, recently there's been a lot of interest in doing fault-tolerant quantum computation for non-Markovian bands. Most of the early work was done for Markovian bands, starting with a paper by Barbara Terhal and Judith Burkhardt, I think in 2007. People became interested in the non-Markovian case, and these noise strength type quantities show up in that analysis. Very similar to what you're seeing here. Okay, so in fact, the string of inequalities is relevant in that context as well. Okay, so now let's go back to dynamic decoupling, and I just want to motivate this by saying that on the left-hand side, what I have is some kind of a measure of success of the dynamic decoupling procedure. How well was I able to preserve the ideal? How well was I able to get, how close was I able to get to the ideal state in terms of my actual state? Okay? What's the distance between my ideal state and the actual state? In the case of Hahn's spin echo experiment, the distance was rather large. We need to do a lot better than that. And if I can show that on the right-hand side here, I have something small, then I'm in good shape. Okay, so the goal is to reduce the effective Hamiltonian or the nose strength. And the method that I'm talking about, of course, is dynamical decoupling. So the question is, how do we compute this effective Hamiltonian? For now, it just seems like some kind of an abstract entity. And it turns out that there is a tool called the Magnus expansion, which is the cousin of the Dyson series of time-dependent perturbation theory, which is designed just for that purpose. And the Magnus expansion is the following. You have a Schrodinger type equation, first order linear differential equation, operator value, and you write the unitary in terms of what I call the effective Hamiltonian. You expand it as an infinite series, and then the Magnus series, Magnus expansion, tells you what the terms of this series are. Okay, so for those who are familiar with the Dyson series, Dyson, you actually expand u of t in powers of t. Here you're expanding the Hamiltonian, the effective Hamiltonian in powers of t. So it's like a cumulant expansion, for those familiar with stat math. Anyway, the first Magnus term is just the average of the Hamiltonian over the time that we're considering. Okay, so this is the term that is made zero by dynamical decoupling. By all these dynamical decoupling sequences that I've shown you, this average was actually made zero. But there are higher order corrections, omega 2 and up, and these involve commutators. Okay, and then the third order term, if you think you can guess the third order term, you're wrong. The third order term is actually nasty looking, and unfortunately the higher order terms are get nastier and nastier. They involve the Bernoulli numbers and some sets of nested commutators, which you wouldn't be able to guess. But nevertheless, they're known systematically, and there's some recursive formulas for writing them down. So we can compute this H effective to any order we wish. All right, so that's the end of the detour. Now let's go back to dynamical decoupling. And now let's look at dynamical decoupling in a general way. So what is dynamical decoupling? The general way, inspired perhaps by this idea of putting the Hamiltonian on the vertices of the tetrahedron or some more general object, is that you have some sequence of pulses. In fact, let's assume for simplicity that we have a group of pulses, which I'm going to call GI. And we're going to apply these pulses in the following way. First we apply G1, then we have free evolution. F stands for free evolution for time tau. Then G inverse, G1 inverse. Now we apply the next pulse, G2, free evolution, G2 inverse, etc. until we exhaust all the members of our group. Okay, so the actual pulse that is being applied is G1, then G2, G1 dagger, etc., etc. Okay, but it's useful to decompose it in this way. Now we can use the Magnus expansion. It may not be totally obvious, but actually you can just think of the BCH, the Baker-Campbell-Hausdorff expansion, if you're more comfortable with that, in order to get the first order contribution, first order in tau, which is just this sum of the G's applied to H. Okay, higher order terms are present. I haven't written them down. They involve commutators. They will be ordered tau squared and higher. Now, let's choose these pulses, these rotations on the Gauss sphere, so to speak, such that this term is zero. Okay, so given a system math Hamiltonian, let's say somebody gives you some information about the system math Hamiltonian. You know its algebraic form. You know that it is a single qubit coupled to a vector. And you know what the most general form of a single qubit system math Hamiltonian is. All right, so with that knowledge, you can try to design pulses such that this so-called group average is 0. That's the idea of general dynamical recovery. So we eliminate the first order term in tau. We haven't yet necessarily eliminated higher order terms in tau, and we're going to go there. But first we have to understand how to eliminate the first order term in tau. All right, so how does this work for a qubit? What is the most general thing that can happen to a qubit? The most general thing that can happen to a qubit is has a system F Hamiltonian, which involves sigma x, sigma y, sigma z. Right? Nothing more general than that can happen to a qubit. Well, it turns out that if you choose as the group of pulses here, if you choose the Pauli matrices, including identity, in order so that it is a group, and you follow this recipe, the very same recipe that I wrote down. Okay, so here I'm just going over the entire Pauli group of a single qubit, I, Z, Y, and X. It turns out, and it's easy algebra to show this, it turns out that this group, this averaging, is sufficient to satisfy this condition, the first order condition, no matter what the system F Hamiltonian is, on a single qubit. Okay, so this generates enough sign changes that all add up and cancel that this condition is satisfied for a single qubit, totally general. Okay, so the Pauli group, which in this context is also a universal decoupling group in some sense, eliminates arbitrary system F interactions to first order on a single qubit. And if you want, you can simplify this sequence a little bit just by taking advantage of Pauli matrix identity. So y times z is x, and x times y is z. That's why I can write it as x, z, x, z. Okay, so remember that magic sequence, x, z, x, z. It's the Pauli group averaging of single qubit decoherence. X, z, x, z is known as the universal dynamically coupled pulse sequence, because no matter what the coupling is to that single qubit, it will average out the BAF, the system F coupling to first order. This is a very important little pulse sequence, x, z, x, z. Here's another way to look at it. X, Z, X, Z, or maybe Z, X, Z, X, where it doesn't matter. Free evolutions in between. Now I'm doing this slightly more realistically. I'm allowing the pulses to have some width, delta. Okay, and in between I have these free evolutions. And if everything went perfectly, I would have, at the end of this pulse sequence, I would have F prime, which would have an effective Hamiltonian that is 0, ideally. Let's say I could somehow cancel all the orders of the matrix expansion. Well, in real life, that doesn't happen. In real life, I have some accumulation of errors. Okay, so the effective Hamiltonian is not going to be 0. It's going to be non-zero because of the higher orders in tau. So the fact that tau is not 0, the fact that there is a distance between the pulses, messes things up. And also the fact that the pulses have width, which I haven't even accounted for yet. These two factors together conspire to make the effective Hamiltonian non-zero. Okay, so now this effective Hamiltonian is the very same effective Hamiltonian that I was talking about when I talked about the three lemmas. Okay, so now hopefully you're starting to see the connection. If I can minimize the norm of this effective Hamiltonian, I can improve my dynamical decoupling performance. So let's consider what happens for the universal decoupling sequence, xz, xz, if I just repeat it over and over again. Let's say I do xz, 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 xz forever. Not really forever. Let's say that I do it for some time, total time, capital T, and that I've used a total of n pulses to do so. So this is the noise strength, the one that bounded from above the Kolmogorov distance. You can show that the noise strength, in this case, is proportional to 1 over the number of pulses. Okay, so let's say that I fix the total time. I'm doing xz, xz, xz for total time, capital T, and now I do it again for the same amount total time, but I squeeze in more pulses and more pulses and more pulses. Well, you expect, of course, that as you squeeze in more pulses into the same fixed total time, you're flipping faster, right? So you expect the performance to improve. You're not allowing the state to evolve. You're constantly kicking it back and forth. You're at time averaging. So the noise strength will go down, and in fact, it goes down just like 1/n, which is okay, but it's not great. All right? So periodically repeating a pulse sequence is not a bad idea, but it doesn't buy you that much. The effort that you have to put into putting more and more pulses into a fixed amount of time, well, you have to put in more power. Right? So there's a cost involved in making this n larger for a fixed total time. So the question is, can we do better? All right, so in order to understand whether we can do better, we have to take a closer look at how dynamical coupling works. And what I want to argue is that dynamical coupling is like a renormalization, or a rescaling, maybe, to be more politically correct. So let's look at what is getting rescaled or renormalized. Let's define two parameters. I'm going to call them J and beta. J is just the norm, operator norm, largest eigenvalue of the system bath Hamiltonian, and beta is the largest eigenvalue of the bath Hamiltonian. Now here's what you're going to show by carefully going through the Magnus series analysis. You can show that after you perform dynamical decoupling, the value of J, the value of the effective system bath Hamiltonian norm, changes. So I'm going to call the bare original one J or J0. After one sequence of dynamical decoupling, we get a new one, J1, the norm of the effective Hamiltonian. And it is given by this expression. Okay, so if you stare at this expression for a moment, you can see that you're going to win if the max of these two terms is smaller than J0. Right? So you start with a certain norm, a certain J0, and if you make tau sufficiently small, what's tau? Tau is the distance between the pulses. So if you make the distance between the pulses sufficiently small, then effective J is going to go down. And it's a competition between these two terms. All right. That's the J, that's the system bath coupling. What about the bath? The norm of the bath itself. The norm of the bath itself always grows, which is kind of bad news. Okay, you might think that it's irrelevant what the norm of the pure bath Hamiltonian is, but it's not irrelevant because there are commutators that couple the system bath Hamiltonian to the bath Hamiltonian. And these commutators play a role in higher order perturbation theory. So this is not good. But this is very good. This tells us that by making tau smaller, we can reduce the norm of the effective coupling. However, the problem is that right now we don't have a way to continue this. When you see this, you're probably thinking, oh great, so now I can just continue this process and I'm going to make the norm smaller and smaller and smaller. But right now we don't have a way to set that to make that happen. This is just one iteration of this universal decoupling sequence. So how are we to continue this? The idea is to borrow from concatenated error correcting codes, and rather than concatenate error correcting codes, how about we concatenate pulse sequences? Okay, so just like in concatenated error correction, we improve the performance of a code by nesting it into itself, and we doubly exponentially decrease the error probability at exponential cost of growth of the code. Now we're going to exponentially increase the size of our pulse sequence and hope that something good comes out of it. So let's do this concatenation of dynamical coupling sequences. Here is the first level sequence, XZ, XZ. The one that I showed you or told you is a universal decoupling. So how are we to concatenate it? Well, the idea of concatenation is to replace every free evolution by the previous level pulse sequence. So this is obviously a recursion. Right? And for level n plus 1, you would just insert level n between xz, xz. So this is a recursive way to construct a concatenated pulse sequence. All right, so you can start writing down what these pulse sequences look like, just for fun. And they grow very quickly, obviously. So here's unconcatenated, level 1. This is what happens if you calculate P2, insert P1 into itself. So you get a sequence that has basically 4 squared, 16 pulses. You can simplify it a bit. That's why you see Y's here if you look carefully. So it's a little less than 14 pulses. You can do it again, and you're going to get 4 cubed, 64 pulses. You can simplify it a bit. All right, so, okay, cool. So we have concatenated pulse sequences that grow exponentially. So is this any good? I mean, can we really expect something like what happens with concatenated error correction codes that we're going to gain by this construction? Well, so remember that idea that dynamic decoupling is like renormalization. It renormalizes the system path coupling. The idea behind this is to continue the renormalization. Okay, so to see in detail how that works is not something I will attempt to do in the limited time I have, but I will just tell you that in fact it works. And in fact, this construction of concatenation precisely has the effect of shrinking the error, if the error is less than 1 in some sense. This is the noise strength, really, which is being shrunk here. In some sense, doubly exponentially, just like what happens in error correction, but not quite as good. Okay, so here's what really happens. For a concatenated pulse sequence involving a total of n pulses and taking a total amount of time, capital T, this is the new noise strength at the end of the sequence. Before I talk about this, just remember, we got the expression for the noise strength after n pulses if we just do the periodic sequence, the periodic VT, which is XZ repeated over and over again. There, the noise strength went down like 1 over n. Turns out that for the concatenated sequence, the noise strength has a bad term that grows, but it has a great term here that shrinks, like n to the negative log n, and c is some positive constant, and b is some other positive constant. Okay, so for large enough n, this definitely beats the 1 over n. Okay, so yes, so the concatenation actually does something good. All right, if you don't believe me, let me show you some experiments. By the way, we also did simulations on this, but I'd rather show you the experiments. So Peter Suter from Dortmund has performed concatenated DD experiments. And you know what, before I talk about this, is there anybody who understood how the concatenated sequence works, or what it is? I didn't ask him, nobody understood. I asked anybody. Did anyone understand how the concatenated sequence is constructed? Okay, I see some. Yes. Okay. Who does not understand how the concatenated sequence is constructed? You guys are just like my first year algebra students. Too shy to even say a word. Come on. All right, feedback. Who understood how the concatenated sequence works? Okay, thank you. Who did not understand how to construct a concatenated sequence? Okay, I do see a couple of hands. Okay, so I don't want to keep going until this is clear. So let's try this again. Here's how it's constructed. You take a sequence and you just replace the free evolution periods. Here's the pulses, X, Z, X, Z. These are pi pulses. So these are rotations. Bang, bang. In between these rotations, we have free evolutions. And what you do is you take this sequence and you insert it into itself in this way. That's the level 1 recursive construction. And then you keep doing this over and over again. Okay? So let's see what it looks like over here. Here's the first sequence. So what do? I take this F and replace this F by the entire sequence. Okay, so here it is. F got replaced by the entire sequence. Let's see if we can find it. Well, we have this little problem for Y here. Let's read it from right to left. FZ, so look for ZX, ZX. Oops, there's no X because X got multiplied by Z here, which turned into a Y. I don't know if that helps, okay? But you can see this sequence almost here. Zx, Zx. And then you do it again, and again, and again. All right? Is that clear? Great. Okay. So this is how we make a concatenated sequence.
I mean, why does this work?
Sorry?
I mean, why does this work?
Why does it work? It works because you can think of the output of the level 1 sequence as the input to the next level sequence, and that output of the first sequence is already small. The next level sequence takes something small and makes it even smaller. And this continues and continues, provided that you're in the right regime. Okay, this is not some kind of magic book. You have to be in the right regime, which basically you can see from here. Okay, these parameters have to be, both of these have to be smaller than 1. Okay, so for a fixed tau, for a fixed pulse interval, you can't have a norm of HSP which is too large. This has to be less than 1, and this has to be less than 1. So if to begin with, your norm strength is sufficiently small, then this procedure will work. You get an attractor. It's like a dynamical map with an attractor. All right, so here's the sequence. Here's the error scaling, the theoretical error scaling, and here's the first experiment. The first experiment is an NMR experiment done by Lidar. On a single qubit, the molecule is adamantine. This is the molecule. The green bulbs are carbon atoms. The white ones are hydrogens. The one in the middle is isotopically labeled carbon. It's carbon 13, so it has spin 1/2. The other carbons are carbon 12. They have spin 0. And the hydrogens are spin 1/2, so they are the environment. All right, so you have this carbon qubit in the middle, which is experiencing the environment provided by the hydrogen atoms. And then they ran the concatenated sequence. Okay, so this is what it looks like. These are the results. So the echo intensity, this was some kind of a measure of coherence. The higher this echo intensity, the better it is. This is like the spin echo. How high can we make the spin echo? As a function of time. And let's start from the worst case. So here, the pulse interval is large. It's 85 microseconds, which is, for that system, turns out to be a large pulse interval. Large pulse interval is not good. We want to make the pulse interval as short as we can. All right, and then the blue curve is the periodic repetition of XZ, XZ. And the red curve is the concatenated sequence, and they went out to concatenation level 3. Okay, so they went up to a total of 64 pulses. Yeah?
When you say large, what are you comparing?
You have to compare it to the norm of the system Bath-Hamiltonian, the norm of the Bath-Hamiltonian, or if you wish, you can compare it to some kind of a high-frequency cutoff in the Bath spectral density. All right, so in this case, with a large pulse interval, the red curve, concatenated curve, is not any better than the blue curve, the periodic sequence. But if you start to make the pulse interval smaller, you see that the red curve starts to perk up. And if you make it even smaller, the red curve is almost flat. Yes?
You said they use 64 pulses for the red curve. Do they also use 64 pulses of just the alternating XZ for the blue curve?
Exactly. Yeah. So for sufficiently small pulse interval, we have a spin echo, which is rather high. Okay? So that's one set of experiments. It shows that as you increase concatenation level and as you decrease the pulse interval, things get better, like we hoped. Here's another experiment, totally different system. Here the qubit is an electron spin, and it's the electron of the phosphorus donor in silicon. And this is isotopically purified silicon. So there's the silicon 29 is what gives you the spin bath. And there's about 1% natural abundance of silicon 29 in silicon substrates. So you have one out of every 100 of these silicons is actually a nuclear spin bath. The other ones are spin 0, so they're not about, they're just there. And then these are the transitions. These are microwave transitions. One of the blue transitions here, which flip the electron spin, is what was used to implement the dynamic decoupling sequence. All right. These are the results. Periodic sequence versus concatenated. Here is the periodic, here is the concatenated. This is, once again, the echo as a function. Now this is as a function of the, okay, you can see it here as a function of time, 50 milliseconds, 100 milliseconds. The number of repeats is now just the number of times each, the periodic sequence is repeated, okay? So 5 means 5 times XZ, which is 5 times 4, 20 pulses. Here it's plotted as a function of concatenation level, which is like log time. All right? Now, you see that when you do the periodic sequence, let's forget the difference between blue and red for a second. When you do the periodic sequence, the echo intensity falls off as you do more and more repeats. So it doesn't actually help you to repeat the periodic sequence. Makes matters worse. With the concatenated sequence, the intensity, echo intensity is basically flat. They went up to concatenation level 4 and they ran out of pulses on their pulse generator. So this is other evidence that the concatenated sequence outperforms the periodic sequence. Now, what's the difference between red and blue? It's the difference in the initial state preparation. The plus x, the red, is when the system is prepared in the sigma x eigenstate. So it's 0 plus 1. That's the Q. And the plus y is 0 plus I1. Right, so 2 perpendicular states in the xy plane on the Bloch field. So this shows that this situation is in fact insensitive to initial state preparation as well. All right, so the concatenated sequence does a good job of preserving coherence. Much better than the original Hahn echo for sure. Yes?
Yeah, so to me it looks as if these Ball sequences almost work better than they should. So my question is, the theoretical prediction for scaling was based on the assumption that the pulses are perfect.
Yes.
But they will not be. I mean,
Right.
Sometimes you're over-rotating by a degree, sometimes under-rotating.
Mm-hmm.
What is the effect on those over and under rotations on the scaling of the procedure, on the scaling of the error?
Random over and under rotations cancel to some extent. Systematic do not, and destroy the performance of the sequence. And in fact, and this is seen in the experiments. Okay, this experiment was very careful, and these pulse generators are very good. The NMR experiment was not as good, and you can see that what you're saying is that they almost work better than they should, but you see that even for this very short delay time, the coherence does go down.
Mm-hmm.
Okay, which is primarily due to these imperfections that you're talking about. In the Lion experiment, he just hasn't reached the limit where that starts to show up. But you're absolutely right that this actually goes to the heart of the problem with dynamic decoupling, which is that it's not an intrinsically fault-tolerant method. Okay, so unlike error correction, where we can construct methods that are fault-tolerant to pulse imperfections, so to speak, there's no such thing in dynamic decoupling. So at the end of the day, we will actually have to supplement this method with something that can deal with fault tolerance problems. Now there are methods which were developed in NMR known as composite pulse sequences, which were designed to deal with systematic errors primarily. So systematic over and under rotations. Those have not yet been incorporated into these kind of procedures. Perhaps it's a good idea. Okay.
Excuse me.
Yeah.
Just a question about the last one.
Yeah.
So the pulse sequence in the periodic case, that's y, that's 1.
Yeah, in fact it was, but doesn't really matter. Right, yeah. Experimentally, there was some difference, and I never recall exactly what the issue was. For some reason, it's easier for in Lyne's experiment to make a Y than a Z. Okay, so can we do better than the concatenated sequences? Concatenated sequences are sort of pulled out of the hat. They're inspired by concatenated error correction, this idea of a recursion, but they're not designed to be optimal. So, is there such a thing as an optimal pulse sequence? And what does it mean to be optimal? Well, it means that we should be able to remove as much decoherence as possible with as few pulses as possible. Okay? Well, Ulrich found an optimal pulse sequence 3 years ago. And the pulse sequence that he found is totally different from the concatenated sequence. He found it by looking at the spin boson model for pure dephasing. So what has now become known as UDD, Ulrich DD, is a pulse sequence which removes dephasing only on a single qubit. And it does so in an optimal manner. But when I say optimal, what I mean in this case is that every additional pulse removes another order of perturbation theory. Okay, in the concatenated DD, the CDD case, that's not true. It's not true that adding a pulse removes an order of perturbation theory. What is true is that adding a level of concatenation removes an order of perturbation theory. But here it's one extra pulse. And the way that's done is by playing with the pulse intervals. So what Ulrich discovered was that it's a good idea to work with non-uniform pulse intervals. And he was actually able to analytically solve the problem of finding such a pulse sequence for the spin boson model. Again, this is for pure dephasing, not for full decoherence. And then a year later, Yang and Liu were able to show that this Ulrich sequence, the UDD, is in fact universal in the sense that it doesn't apply just to the spin boson model. It applies to any kind of pure dephasing model. In fact, it applies also to pure relaxation. Not, I don't know why they put and in the title. It should have been or. Dephasing or relaxation, not and. So their paper is a very nice read. The proof is somehow trigonometry, and you will see in a moment why trigonometry, because the way that Greg finds his pulse intervals is based on a simple trigonometric formula, just sine squared or something. So, not to be outdone, Ulrich followed with a paper that showed how to eliminate general decoherence on a qubit, not pure dephasing. Like what CDD does, like what concatenated decoupling does, it works with general decoherence. And in fact, Ulrich used the concatenation idea and combined, using a concatenated structure, which I don't want to get into exactly, he combined a sequence that eliminates pure dephasing and a sequence that eliminates relaxation, or T1, T2, in the term Muhammad used. And he showed that this sequence is better than the concatenated sequence that I talked about earlier. It's quadratically better. Not to be outdone, a year later, was it? I guess. We came up with a pulse sequence that does better than Ulrich's concatenated UDD. It's called CUDD. So now that you get into this zoo of pulse sequence making switches, there's hundreds of them. Okay, so this is going to be very confusing, but our pulse sequence is called QDD for quadratic decoupling. And this pulse sequence is actually a nesting of two Ulrich sequences, of two UDDs, in order to eliminate general decoherence. So we eliminate general decoherence. And the way it's done, it's actually exponentially better than Ulrich's concatenated UDD. And the result is that with n squared pulses, you can eliminate the first n orders of perturbation. Okay, so for UDD, which was for purity phasing, the first one, the one from 2007, with n pulses for purity phasing, you could eliminate n pulses, eliminated n orders of perturbation. Now, with n squared pulses, more pulses, however, we do a lot more, we eliminate general decoherence to n order. Right. How does that compare to concatenated DD? Well, instead of n squared pulses, concatenated DD needs 4 to the n pulses. Okay, you need n levels of concatenation. Every other level multiplies the cost by a factor of 4. So, what does this look like? All right, so here, remember the trigonometric formula that I mentioned? This is Urg's magic formula. J is an integer that runs from 1 to n. N is the number of pulses that you're using. N is also the number of orders of perturbation theory that you're going to eliminate. And Urg found analytically, again, using the boson model, then Wang and Liu showed generally, that if you space your pulses, just z pulses, let's say, or just x pulses, let's say, at these intervals where t is the total time, so sine squared, those are the Urg times. Those are the magic times that eliminate pure dephasing or pure dissipation to n order using n pulses. In QDE, where we nested the two Urg sequences, we add to the z pulses at these times, we add x pulses because we have to eliminate not just dephasing, we also have to eliminate dissipation. At times which are basically a nesting of two Urg sequences. It might be a little hard to see from here, but if you look at it for a moment, you'll understand. This is just a nesting of two Urg sequences. Here's a nice graphic way to look at the pulse times. So, yellow is free evolution, green is free evolution conjugated by y pulse, blue is conjugated by x pulse, etc. Now, each one of these diagrams tells you for a given number of pulses, let's say here, and it's 4 pulses, what the pulse sequence is. The pulse sequence is yellow is free evolution. Okay, the area here is the interval between pulses. So apply free evolution for an area that's yellow, then apply xux for this area, etc., and read it off going row by row. So you walk down this diagram. Okay, that's the pulse. I hope that helps. If not, use the formula. All right. So how well does this do? Here are simulation results. So these simulations were done for a spin bath. Here's the Hamiltonian. It's on a single qubit. Okay, single qubit coupled to a spin bath. 2 parameters to make it simple. Beta is the norm of the system bath, the bath Hamiltonian. J is the norm of the system bath Hamiltonian. And the bath operators are actually 1 and 2 qubit terms. Okay, so we allow for 3 body interactions, 2 body and 3 body interactions, just for fun. And then we have the parameters J tau, beta tau. So tau is the minimum pulse interval. In these QDD and UDD simulations, the minimum pulse interval, the pulse interval is not a constant. So tau is the minimum pulse interval. And then what we're comparing for this model, which was numerically simulated, not using master equations or anything, just by solving the Schrödinger equation. As a function of the total number of pulses, we're looking at the log of the trace norm distance. This d is the same trace norm distance that I talked about earlier. So you want the distance to be small. The distance between what and what? The distance between the ideal state, where there's no system bath coupling, and the actual state, which is what you get by having the system bath interaction plus applying all the pulses. And this is log base 10. Okay, so the numbers here are, this is 10 to the minus 30 down here. Blue is PED, periodic dynamically coupling, that's just XZ repeated n times. Purple is concatenated DD, that And this is Urg's concatenated UDD, and this is the QDD. So you see that the QDD actually does dramatically better as a function of the number of pulses than, by orders of magnitude, than the other methods, which is the predicted or advertised. You need n squared pulses to remove the first n orders of perturbation. That's what these simulations show. All right, so let me wrap up. I talked in the first half. I talked about how symmetry can be thought of as a unifying principle for various error correction and suppression and data hiding strategies. In the second half, I talked about dynamical decoupling because we saw in the first half that the error hiding, the information hiding strategies making use of symmetries are limited. So we need to supplement them with something else, like dynamical decoupling. So what would be a comprehensive strategy? Well, we could think of taking some kind of a layered approach, where at the bottom layer we start with using up all the symmetry that we get for free from nature. So that would give us a DFS encoding. Right, so this uses the symmetries as much as possible. The problem is, of course, that the symmetry is not for free and it's not perfect. So we need to probably supplement the DFS encoding with dynamical decoupling in order to generate symmetries. Remember the idea of removing the asymmetric piece, leaving just the symmetric piece using dynamical decoupling. But then we have issues, as Robert pointed out, that we have pulse errors. We have another issue which I only hinted at, which is Markovian effects. Dynamical decoupling actually does not work at all when you have Markovian maps. It is designed specifically to exploit the non-Markovianity of a depth. That has to do with the Zeno effect. I mean, I'll go there at this late point. But there is an additional assumption here, which is that the dynamics is non-Markovian in order for dynamical decoupling to work. So we need to, in order to overcome these two remaining issues, pulse errors and Markovian effects, we need to incorporate fault-tolerant quantum error correction. And in this way, rather than just going directly for fault-tolerant quantum error correction, we will probably be able to do better. To save on resources and make more clever use of what nature is giving us. So there are some open questions here, actually a lot of open questions. One natural open question is, if you believe in my previous slide, the question is, what is the optimal hybrid strategy? Okay, how are we actually going to put all these pieces together? That's an open question. Is the order that I propose correct? Maybe there's some better way to do it. Maybe we should put in topological protection. Maybe something else altogether. So, however, it seems clear that using hybrid strategies is probably a good idea, as opposed to just going with a single one. And then another question, which we've actually been able to address in this recent paper, is, let's say you combine dynamical decoupling with fault-tolerant error correction. Does that help you? Can you show that dynamical decoupling really does reduce resources or improve the thresholds? And it turns out that in the right parameter regime, the answer is yes. And for that, I point you to this paper, and thank you for your attention.
So what does it help with the resources or with the threshold value? I mean, there's this CNIL result, 3% error threshold. Can you improve that?
What you improve is, provided you're in the right regime, which is determined by basically norm of system dot Hamiltonian, norm dot Hamiltonian. What you improve is two things. You don't actually improve the threshold itself. What you improve is the strength. So if you have a circuit which, without dynamical decoupling, is above threshold, you can push it to be below threshold. And that's one thing. And even if you are already below threshold, so you don't need dynamical decoupling to push it below threshold, and you can actually significantly reduce the resources. So just in terms of the overhead, a number of extra gates needed. Yes?
So the example in the last review, it seems that the system you couple with the environment is just one particle.
The system is 1 qubit.
Yes, it's
Yes.
1 qubit.
Uh-huh.
So if you have more qubits, so what might the situation become?
Right. You mean, can you use dynamical decoupling when you have more than a single qubit?
Yes.
Yeah, so the answer is yes. And I don't know if Pablo is still here. Pablo is still here? Okay, he actually worked on this problem of coming up with sequences that decouple multiple qubits. There are some very elegant ideas there using Hadamard matrices, orthogonal matrices, for coming up with efficient pulse sequences. So the answer is absolutely yes. You can use dynamical decoupling to decouple more than just a single qubit. Yes?
Is the role of the X and Z dimension a unitary evolution or I believe it can.
In dynamical decoupling? When I said X and Z dynamical decoupling, I probably was using them in different contexts in different ways. But when I say an X pulse, I mean a unitary. Okay? So yeah, so it's a unitary.
So if the X, for example, if the X is the evolution created by the pulse, what is the problem that the pulse has a finite time?
What's the problem? Okay. The problem is that the pulse is imperfect. Why is it imperfect? So here's the pulse. Let's say it's on for some time delta. Now what's really on? In an ideal world, what would be on is just some system control Hamiltonian. But in real life, what is on is a full Hamiltonian. Right? And this is not equal to this. This would be, this one is the ideal. This is what you get in real life. So that's why you have to make your pulses narrow. Or use some tricks to compensate for the errors due to these terms.